start it now. All right, 3, 2, 1, go.
Welcome to our Search for Solutions group project on solar power satellites. I'm Patrick Hogan.
Austen Fourkas.
And I'm Justin Dasuki.
So essentially, a solar power satellite behaves similarly to a solar farm on the surface of Earth, except because it's in space, it can capture a lot more solar radiance because there is no atmosphere to absorb a lot of that energy. And then that power is transferred to the surface via wireless power transmission, or WPT, which is essentially using microwaves or lasers.
So how solar power satellites work, there's basically two types, but it all starts with one, which is the satellite that is programmed to follow Earth's orbit. One of them is geostationary Earth orbit for microwave transmissions and low Earth orbit for laser transmissions. Both technologies capture the sun's radiation and converts it to direct electric current using mirrors spread across space that reflect the sun's radiation directly onto the solar panels attached to the satellite. The satellites also utilize photovoltaic arrays and would be structured to face the sun at all times in order to capture as much energy as possible. Places like the ISS or locations on Earth then gather the captured electric current wirelessly through the use of WPT. Eventually, the electric current is sent back to the ISS or power receiving stations in the form of microwave or laser transmission energy. This is ultimately the base ingredient that is converted into electricity. The last step is converting the inputs into electricity at the power receiving stations that convert the energy and input it into electrical grids that can be utilized by single buildings all the way up to entire cities. So how solar power satellites address climate change? For one, it does not emit greenhouse gases when utilized and also does not contain hazardous waste that can negatively affect the environment after that technology has been used. Another is that it does not depend on fresh water or farmland that has become increasingly scarce on Earth. And in essence, the technology is carbon neutral. Since this is a very recent technological advancement as a whole, the production of the spacecraft, launch vehicles, and space infrastructure will largely already be carbon neutral. The inputs and supporting activities are largely absent of containing fossil fuels and utilize reusable, environmentally friendly energy sources like solar or wind in the manufacturing process. The technology, however, is not carbon negative since it does not actively take away carbon dioxide away from the atmosphere. The picture on the left is the Cygnus space freighter. Although the Cygnus is a spacecraft meant for cargo transport to the ISS and not an actual solar power satellite, the spacecraft contains its own set of solar arrays that are used to capture energy for power generation, storage, and distribution within the Cygnus. Based on the success of the solar arrays on the Cygnus, it can be assumed that solar energy harvestation is very much possible. The only challenge lies in sending that energy back to Earth.
So there are a couple main benefits that spacebound solar panels have as opposed to earthbound solar panels. The first of those is uptime. As spacebound solar panels do not have to adhere to terrestrial weather patterns. So if it's cloudy, it's raining, it's snowing, earthbound panels cannot absorb any photons as obviously there is no sun. But space-based solar panels do not have to be worried about that. In theory, they also have 100% uptime as they can follow the path of the sun and stay stationary in Earth's orbit. Their second main benefit is the efficiency. So the main type of light that gets through the Earth's atmosphere is visible light, as can be shown on the diagram. As the wavelength of light decreases, it becomes higher energy. So the next higher energy steps are ultraviolet, gamma, and X-ray. The sun doesn't emit any high energy events, so gamma and X-rays are out of the question for earthbound solar panel satellites. This is where ultraviolet light becomes very important. As the spectrum towards the bottom shows, the sun does emit a fair amount of ultraviolet light. And the equation in the top right shows that the lower the wavelength of light, the higher its energy, as the wavelength term is in the denominator. So in theory, solar panel satellites will be able to absorb higher energy photons as opposed to just the visible photons that earthbound satellites or earthbound solar panels can absorb. There are a couple of big impacts as well. Solar panel satellites introduce another alternative energy source to the already long list of solutions to climate change, and obviously more solutions are always better than fewer. and it also indirectly furthers other extraterrestrial technology, as most of the necessary technology for space-based solar panel technology is not invented yet. There are a few accomplishment barriers and costs, however. Repairs to space-based technology are extremely complicated and costly, and if you don't have a crew living on satellites, it will be difficult to get them up there annually or biannually or however long they need to get up there. And if solar power satellites ever become mainstream, the concept of space property may become difficult between countries with troubled relations.
So a huge drawback of this entire solution is the cost. And that mainly hinges on the fact that solar power solar power satellites and really any spacecraft carry huge price tags. And on top of that, you need to be worried about maintenance and repairs, as Austin had on his previous slide, as well as creating receiver stations around the Earth and connecting those to already existing power grids or possibly even new power grids. So essentially, the overhead cost will be huge, but the payout may be great in the long term.
So in summary, solar power satellites are an emerging technology that gathers solar radiation from solar arrays connected to spacecraft and then ultimately converts that solar energy into electrical energy. Among the pros, the one that needs to be highlighted the most is that there's unlimited slash high energy potential source since we utilize the sun when we use solar power satellites. However, among the cons, the biggest one has got to be the overhead costs that is preventing solar powered satellites from being used all over the world. And as a group, we believe this is a great option to combat climate change in the future. However, given its enormous costs and the options readily available present day, we believe this technology should wait to be utilized for now. The best way is when technology is able to keep up with the solar power satellites.